Good morning, students. As you know, in the last class, we have discussed the various parameters which affect the Mössbauer spectrum. And in that context, we had discussed isomer shift in detail. What are the things that can affect isomer shift? There is s electron density and covalent bonding nature of. So all these things have been discussed in the last class. But we missed out on the other two parameters, that is quadrupole splitting and magnetic hyperfine splitting. So these two things are remaining, and I am going to cover all these 2 points, all these 2 parameters in today's discussion. So So today we are going to discuss the electric quadrupole interactions and the quadrupole splitting that results in case of Mossbauer spectrum. So a quadrupole, as the name suggests, is a collection. A dipole means there are 2 poles. A this term quad means 4. So this term will basically mean that we have 4 poles in a nucleus. So such quadrupoles arises when you have spin quantum number is greater than half. Then we have asymmetric non-spherical charge distribution within the nucleus, which gives rise to this quadrupoles. As you can see, if the spin is half, spin quantum number is half, then the nucleus is spherically symmetric. There is no separation of charges within this nucleus, and so there is no quadrupole generated. But if you have spin quantum number greater than half, then the charges, you can see plus plus minus minus will separate out, and in this manner within the nucleus. And so this minus charge is coming from where? This is due to the s electron density. S electrons have maximum amplitude. The wave s electron has maximum amplitude at the nucleus, and so that's what we are seeing over here. That's how so this is an effect that you will see. So this is how you are getting 4 poles, 1 2 3 4, plus minus. So in a dipole there are 2 poles, in a quadrupole there are 4 poles. So this kind of thing can arise in a non-spherical nucleus having quantum number greater than half. And this interaction, this quadrupole interacts with the electric field gradient. There is a special term here which we are talking about, electric field gradient. We will discuss more about it. So, and this interaction results in the splitting of the energy levels, nuclear energy levels. So, this quadrupole, the concept of quadrupole is very important in the sense that it is implicated in this Mossbauer spectroscopy. You are already studying it, and the same concept will be useful in case of nuclear magnetic resonance, NMR, electron paramagnetic resonance, EPR, and NQR spectroscopy. So this is important. You must understand this. So a dipole was a vector that you know, and here, because it is a 3-dimensional thing, a quadrupole is a 3-dimensional thing. You can't simply describe a quadrupole using a vector. A vector has a magnitude and direction, but you need a third thing which is called tensor. A tensor is something that in which you have to specify the magnitude, direction, and the plane on which it acts upon. So we need to have a tensor to describe this kind of situation. This is quadrupole which is generated in the nucleus, and this nucleus in this, the value of q that we are talking about, the quadrupole moment. So a quadrupole moment, a dipole moment is a vector, a quadrupole moment is tensor. A quadrupole moment in the same, it's basically flowing from the same idea as in dipole moment. You calculate dipole moment, and here you will be calculating the quadrupole moment, but the quadrupole moment will be slightly complex because of three-dimensional nature of the representation, and that is called a tensor. So a non-spherical nucleus may have this kind of situation. It might be slightly elongated along this z-axis. This is what we call as prolate, and in this case the q, the quadrupole moment, is greater than 0, that is, it is positive. In case of oblate, that it is flattened along z-axis, then you will, as compared to a sphere, if it is flattened along the z-axis, then it is this is oblate, and you have the value is negative of the quadrupole moment. And so this is the classical definition of a quadrupole moment given by this. And this is the, and this classical definition it describes Liparsky how to what extent the geometry has departed from the spherical symmetry. So this is what is described by this equation, and this is to take into account the quantization aspect, that what is necessary here. The basic concept is that a nucleus can take different conformation, rotational conformation. It can have different rotational conformations in a asymmetric electric field. So in that case, you need to take into account there are certain orientation that it can take up. There are other orientation which is not possible. So as you remember, in case of rotational spectroscopy, we had discussed this K, the projection of rotation dipole moment vector, and similarly here also you have a two terms. One is I quantum number. This is giving you the total spin of this electron, and the nucleus, and K is the projection along z-axis for this quadrupole. So this quadrupole moment will be oriented along z-axis. It can have certain orientations allowed, not allowed, depending on the value of K, and that gives rise to this quantum number K. So there's another point that is important, is that you can have two ways in which you can place. If you have suppose you have a distribution of charges around nucleus in this manner, and so there are two ways in which you, as you can see in the picture, in these two pictures, there are two ways in which the same nucleus can be put. If you are putting it this manner, then the overall positively charged, this positive charge of the nucleus is facing the positive charge. This is less stable, but in this case, when it is oriented in this manner, it is facing the long end of this ellipsoid that you are seeing, faces the which is positively charged, faces minus charge, negative charge. So this will be a more stable orientation. So this is the point that I was highlighting, that it will take up certain orientations, and this information is contained in this quantum number K over here, which is shown over here. So basically it deals with we are dealing with different conformations of that a nucleus can take up when a non-spherical nucleus can take up in a non-symmetric asymmetric electric field. So there's one more point that we need to consider. Suppose we have a symmetric electric field, and you place in a symmetric electric field you place a dipole. If you have a dipole, it will there will be interaction. The forces will, you calculate the forces, you will find it, and then you sum it up. You will find that overall the electrostatic energy increases. In the same symmetric electric field, if you place a quadrupole like this, then you will find that there is no change in electrostatic energy, because there are four charges, and if you calculate the force, then you can also calculate the torque generated. So eventually all these, in a symmetric electric field, in a quadrupole, all these, the summation of these forces and torques all cancel out, and there is no net increase or decrease change in the electrostatic energy of the system. However, this quadrupole will be affected by the rate of change, the rate at which, with respect to the distance, how electric field changes, the dE by dr, dx, dy, dz, what, that we can define. So, that is what we call electric field gradient. We not only need to have an electric field at the nucleus if we want some interaction, we also need to have a gradient. There should be a change with respect to the change in the Cartesian coordinates. So if that is present at the site where nucleus is located, then there is going to be an interaction, there is going to be a change in electrostatic energy. So this is an important point we need to consider. So that's electric. So this is electric field gradient is a ground state property of solids, and it can be defined as a second derivative of the potential or first derivative of the electric field. So that's what I was saying, that if you are considering the electric field, it's how it changes with change in distance r, dE by dr, dE by dx. That is important over here. If there is symmetric electric field, then electric field may not be zero, but dE by dr can be zero in case of symmetric electric field, and you do not have any interaction with the quadrupole. There is no change in the. So electric field gradient is a tensor. Tensor, again, as I told you, that it magnitude, direction, and what else? The plane in which it acts upon is also has to be specified. So this requires for a vector you will require 1 by 3 sorry 3:1 3 by 1 matrix, but here you will require to describe a tensor, you need to describe you need to have a 3 by 3 matrix. So there will be total of there are 3 elements in case of a vector. There will be 9 elements. There are going to be 9 elements in the matrix that we will use for a tensor. So this tensor is sensitive to the charge distribution. So this electric field gradient, the tensor that we are talking about, is sensitive to the charge distribution, that electronic charge distribution around the nucleus, as well as the nearest neighbor distance and the distribution. So if as you move away from this cubic symmetry, there is bound to be an electric field gradient is likely to exist at the nucleus, and that will give rise to such interactions as we were talking about. And so because of, so this is what we are describing here. An electric field can be considered as a first derivative of the electrostatic potential, whereas a second derivative of this potential gives us the electric field gradient. Okay, so and this 0 comes because the r is 0, the nucleus is our origin point. So this is at r, when r tends to 0, this is the what is the change in electric field with change in distance, that has to be calculated. And if it is non-zero, then and the nucleus is also non-spherical, you are going to have an interaction leading to between the two, and that will give rise to some electrostatic energy. So electric field gradient interacts with the quadrupole, gives rise to and this interaction will change. So what will happen? This interaction will change the nuclear energy levels. It will split up the energy levels basically, and that splitting will be shown in the next slide. So here it is important to note that the electric field gradient that we are talking about it has two components. One is due to the nucleus. You're having nucleus within an atom, and there's atoms in there's several atoms within a lattice. So the overall from an, if you nucleus as a taking nucleus as your reference frame, you will have surroundings can be described in terms of internal atomic electron charge distribution. So that is valence contribution. So electronic charge distribution within the atom, and then distribution of this the charges outside the atom, that comes in the domain of this lattice EFG. So we have lattice contribution called as lattice EFG, and we have valence the electronic contribution within the atom, that is valence EFG. So so these originate from outside the atomic sphere, and valence contribution within the atom. So this valence EFG can be further decomposed into partial wave functions, that is P, D, PF and FF, and this decomposition corresponds to the occupation of these orbitals. So the distribution of electronic charge within the atomic sphere dominates the electric field gradient. So lattice component of the electric field gradient is small as compared to the valence shell electronic component. So this is how we usually represent electric field gradient. This is del del E, first derivative of the electric field, or which is also can be taken as a second derivative of the potential. And so a matrix representation will be like this, having 9 components. However, there are only 5 terms which are more important, and the most important is the VZZ term. And usually everything finally simplifies to this, which we will be using in the next slide. So in the presence of electric field gradient produced by asymmetric electronic charge distribution or ligand arrangement, the nuclear energy levels are split, and the splitting of this in case of iron is or tin, which have the excited state is I is 3/2, so it is greater than half. In this case, you will have the splitting will be in the order Mi plus minus half, Mi plus minus 3. So you can see here that the splitting that here takes place does not distinguish between plus half or minus half, or plus 3/2 or minus 3/2. It only depends on the magnitude of this quantum number, magnetic spin quantum number, which only the magnitude of spin quantum number is important, not the direction. Okay, so this is what is going to happen. So now if you have the ground state I is equal to half, it has the charge distribution within the nucleus is spherically symmetric, there is no splitting. But when it goes to excited state, if you consider the nucleus in the excited state, the charge distribution becomes asymmetric and non-spherical. So when it interacts with the electric field gradient, it will split up into these two energy levels, plus 3/2 and so plus half minus half altogether. So this splitting is shown as del EQ, is the quadruple splitting parameter del EQ. So what is your visualization? These lines, see at these lines, this curvature. If suppose it would have been we would have represented an electric field by a straight line, then it would have symmetric. The first derivative of the electric field would have been 0, because it curves when there is a curvature here. So at the nucleus, when you are calculating it at the nucleus, at these points, you have a non-zero value of the electric field gradient, and so that electric field gradient can interact with this quadrupole. So what will happen? So because of the interaction with the quadrupole moment of this nucleus, the quadrupole moment vector will start moving along at it will take up a certain orientation at the particular angle, it tilted along a particular, and then this vector, the quadrupole moment vector, will start moving along this circle. So this kind of motion is called a precessional motion, right? So a quadrupole moment precessing around the electric field gradient tensor that we are talking about. The direction of the tensor is this. So if this is the direction of the EFG tensor, around this tensor, this is how it will move around in a circular path with keeping the angle with it constant, and this is what we call as precessional motion. This precessional motion, you will encounter this term in many in NMR, in ESR, in all these cases. So this is important to understand. So when it takes up this arrangement, and the energy levels are split up in this manner. So okay, so this is sometimes it is also shown by simply a delta sign, and the magnitude of splitting delta is related to the nuclear quadrupole moment we just talked about. So the EQ, the quadrupole moment, and this is so the component that I told you is the most important one is VZZ term. So this ZZ by 2, this is what gives us the magnitude of the other terms are of very low values, less important as compared to this term. So by considering this, you can get the almost a very you can get a very good idea of what the splitting magnitude of the splitting would be in a species. So when the species when this happens, and you allow the electrons, the nucleus, to be excited by you provide the gamma ray of sufficient energy, then they absorb that energy. So you have a dip here, you have a dip here also at a higher energy, so at an increased energy, which is shown by increased velocity of the slide. So this is how what you obtain in a higher velocity side, lower velocity. So both represent the energy level, how the gamma ray energy has been shifted with the Doppler effect by moving the source, and resonant absorption occurred at two different velocities, and so you are getting two peaks. In absence of quadrupole field, remember, you would have only one absorption, which would have been this, and this one, the first point, shows the isomer shift. So now we come to this magnetic dipole interaction and magnetic splitting. Again, the pictures you will see here, this is very common thing you will encounter in nuclear magnetic resonance, EPR. This is the magnetic field. At that point, in previous figure, we had electric field around which electric quadrupole moment was precessing. Here it is the magnetic moment of the nucleus, which will start precessing around the applied magnetic field. So this is magnetic dipole of the nucleus, and magnetic dipole of the nucleus, and in an applied magnetic field it will start moving along this circle with keeping this angle constant. On certain orientations are allowed energetically. So this straight line, we are talking about symmetrical fields. If you draw a straight line like this, the field is symmetric, that's what it indicates. So if you imagine lines would have been similar in case of previous discussion, quadrupole thing, then you may not have any effect on the quadrupole in the previous case. So however, the picture may be similar, but here we are talking about magnetic interactions. That was an electrical interaction, electrical components, and these are the magnetic components of the system that we are talking about. So when you apply this magnetic field, you can see that energy levels are split up. The plus 3 by 2, minus 3 by 2 are split up from the this barycenter. If you consider this center of gravity or barycenter that you call, by the equal energy, and plus half minus half is split up by equal energy in this manner. So this happens when you apply an magnetic field. The magnetic field could be generated due to internal motions of electrons within this. There will be internal field due to the spinning motion of electron, and there will be internal electric field due to internal magnetic field due to the orbital motion of electrons around the nucleus, and all these things will contribute to the net. So even if you do not apply any magnetic field, external magnetic field, there is likely to be an internal magnetic field within the nucleus. So this is also called hyperfine magnetic splitting. Uh, so in so this a typical name that you have heard from your 11th 12th classes also, Zeeman splitting. Whenever they are splitting in the spectral lines, when you are on application of magnetic field, that is Zeeman splitting. Whether it's electronic spectrum or nuclear, it is the basic concept remains the same, so same name can be used. There are many sources of magnetic field that we just discussed. So there is internal field, there is applied external field. So in the internal field has three components: the contact, H contact, that is H is the magnetic field due to Fermi contact interactions. This is the orbital, due to the orbital motion of the orbital magnetic moments. You have due to the orbital motion there will be magnetic moment generated, and this will give rise to magnetic field. Then there is third one, that is due to the spinning motion. There is also the electrons are undergoing spinning motion. Magnetic moment will be there, and that will also contribute. So the three components that we are going to talk about. So these are described over here. So in total you will find that the spectrum will be split up into 2i plus 1 energy levels, where I is the spin quantum number of the nucleus. So the Fermi contact is the new thing that we are going to learn over here. The other two things are similar. You have heard about it in your coordination chemistry classes, magnetochemistry classes. So the Fermi contact arises because if there is a net, so you have s electron density at the nucleus. So far we have considered it as a total electron density due to s electrons, but we have not yet considered the spins of those s electrons. So there might be some cases where the spins, a spin up number of spin up s electrons are more than the number of spin down electrons at the nucleus. So if such a situation arises, or vice versa, a spin down number of spin down electrons are more at the nucleus as compared to spin up electrons, then we call it as a spin polarization. So such a situation will be called a spin polarization. So this is called by this is caused by inner field S shells by spin polarization, and by spin polarized, which is inner shell filled S shells, which are spin polarized by partially filled outer shells. so one example we can talk about here is that of S 5 by 2 Fe3 plus electron, where you have 5 unpaired electrons, which can cause this kind of polarization. And when this field interacts with the nucleus, we call it Fermi contact interactions. The fields are generated because of the different spin density at the nucleus. So the picture will look like in this manner. You have a case here. In case of Fe3 plus, you have D5. So this net spin of the 5 electrons together, up spin, there will be the parallel spins, 5 parallel spins by a thick arrow is shown over here. And in the third shell you also have 3s electrons. So these 3s electrons will also have one of them will be downspin, one of them will be upspin, as required by Pauli's principle. So now see this valence shell 3d5 configuration because it is stabilized by spin quantum mechanical exchange, it also the 3s 3d energies are very close to each other. So this electron, the upspin, if one of the electrons which is upspin over here also interacts with this through exchange interaction, there is exchange interaction between this electron in the s orbital, 3s orbital, and in the same shell we have 3d electrons with parallel spins. So this interaction, so this electron, this 3s electron will tend to stay with this in the outer part of with this in the, it will tend to stay in close proximity with these electrons to have a strong quantum mechanical exchange, whereas the other one has a greater chances of being at the nucleus. So there is net spin density at the nucleus will increase uh, because of these 3s electrons. So 3s downspin will have higher spin density, will cause a higher spin density at the nucleus, and so we have, so you can see the electron density of downspin is greater than electron density, s electron density of the upspin electrons at the nucleus, and so the net magnetic field caused will be different due to the spins, and this will give rise to a contact magnetic field. So this is one component that we were talking about. The other two components are similar. You are familiar with already. Spin dipolar interaction, the magnetic moment of the due to the spin of each of the electrons, that will cause. So the previous example that we were discussing, this is what we call as a spin polarization. Okay, increase in net spin density at the nucleus. The second thing is the spin dipolar interaction. Now those electrons will have a magnetic moment of their own, and these magnetic moments will cause an magnetic field at the nucleus, R is equal to 0. And so this interaction, so this magnetic field will be called as HD, denoted by HD. The third one is the orbital dipolar interaction, that is the orbital motion where L is not equal to 0 give rise to an orbital magnetic moment. And so this is something that you can Bohr magneton into sorry, B should have been subscript here. So that is Bohr magneton into the R cube, so expectation values of the angular momentum that you have to take into account, this L. So this is how the orbital magnetic moment, there will be magnetic moment due to the orbital motion of electrons. So this will cause another magnetic field. So there are three types of factors which will give rise to internal magnetic field, and together when they interact, you will have splitting of the energy levels. And so if we look at the internal magnetic field that we have, so in case of para or diamagnetic compound, the internal magnetic field is 0. In case of antiferromagnetic or ferrimagnetic compound, this has a non-zero value. And if we are looking amongst different samples, the maximum highest value is obtained in case of alpha Fe2O3, which we know as a common name by hematite. So it has the maximum highest value of the internal magnetic field amongst all the iron oxides. There's also a special type of things like in a magnetite, Fe3O4, which have Fe2 plus and Fe3 plus ions both. You have two types of magnetic field, internal magnetic field, inverse, because it has inverse spinel structure. Fe3 ions occupy tetrahedral holes, whereas Fe2 and Fe3 sides also occupy octahedral. So half of the Fe3 go into this, and rest also occupy octahedral holes. And there is rapid electron transfer between the two Fe2 Fe3 system. So this gives rise to two different types of internal magnetic field. So this is the kind of splitting that we get due to the magnetic interactions. So magnetic interaction of the with the nucleus. And transition between the excited state and ground state can occur when Mi changes by 0 or 1. So this is the selection rule. This gives so this is how we draw this how we draw this line. That is, you will get the idea from here, from this discussion, that you must first thing is the selection rule, that the change in Mi must be 0 or 1. This gives rise to possible transition for 3 by 2 to from to 1 by 2 transition. So half to 3 by, I is equal to half to I is equal to 3 by 2 transition, which was initially a single transition, now is splits up into 6 different transitions as shown over here, with different depending on the applied magnetic field, the splitting can vary. So if the line positions are related to the splitting of the energy levels, but the line intensities are related to the angle theta between the gamma ray and the nuclear spin moment. So two important points: splitting of the energy levels, line positions, it gives you the what is the strength of magnetic field depends on that, but the line intensity will depend on the what angle the gamma ray and the exciting magnetic field has with the gamma rays has with the nuclear spin moment. Okay, so the outer, in this cases we will get 6 lines. So outer, middle and inner lines intensities are related by it is given by this formula: 3:4 sine square theta by 1 plus cos square theta is to 1. So that you can see, this is 1, this is 3, and this is the variable. So 3, 1, and this can vary depending on the actual value. So what is the angle they make with the gamma ray photons. So it also means that the intensity of outer and inner line is fixed, but the middle one can vary between 0 and 4. Okay, and in a polycrystalline sample, typically what you will find that this applied the when there is no applied field, this is equal to 2, this inner value, the intensity of the inner lines, whereas this is a relative intensity that we are talking about. But in single crystals or when you apply field to this polycrystalline samples, it may happen that the relative intensity will be different, and it will depend on the orientation and magnet. It will. So this is can be different, and it will give you the information about the orientation of the magnetic moment and the ordering. So this is the total picture summarizing all the interactions that we have discussed so far. So first one, this is the initial an isolated nucleus. Then the nucleus in a typical atomic setup is split up. The energy is slightly changed as compared to the reference nucleus. So you have this line. Now this line can split up into 2. This is splitting due to the quadrupole interaction. And the third one, so electric monopole interaction, electric quadrupole interaction, 1, 2, and this 3 is magnetic dipole interactions. So these 3 things are basically responsible for the splitting in a Mössbauer spectrum, and this gives rise to so one line which was initially expected now can split up into 6 lines as shown over here with differing intensity. So isomer shift, quadrupole splitting, magnetic splitting. So 2 of the things can be combined together also, that also may happen. And so usually you will find that the extent of the electric quadrupole splitting is less as compared to the magnetic dipole splitting. The magnetic field is very high, as we have seen earlier in the previous slide, that the magnetic field can be very high, as high as 520 kilo oerstate. So internal magnetic fields are very high, and that, as compared to the electric quadrupole splitting, magnetic splitting dominates, and it is the splitting is a so the figures. So what we have here is that this splitting is a good guide of as to what state the iron is in case of proteins, minerals. So it's a very helpful technique, as as we will discuss in the next lecture, that third part of the Mossbauer spectroscopy, where applications will be discussed. We will come to know that even on Mars it has helped us in detecting the presence of water, in confirming the presence of water on Mars. So it has and we will also learn about how various we will see some of crucial informations about the dynamics of a biomolecular system can be obtained using Mossbauer spectroscopy. So this is all that will be contained in the third part. So thank you all, and please go through all the notes and this lecture series. And if you have any problem, please don't hesitate to ask anything. You can always email me. So that's all for now. Bye.